Hello friends. So, welcome to lecture series on matrix analysis with applications. So, today we discuss about diagonalization. What do we mean by diagonalization of a matrices? So, let us discuss. Now, first of all, before starting diagonalization, let us discuss similar matrices. So, let A and B be two square matrices of order n over a field F. Then A is said to be similar to B if there exists an invertible matrix P such that B equal to P inverse AP, and we symbolically write A is similar to B like this. Okay. So, what do you mean by basically two similar matrices? So, we say that a matrix A, okay, a matrix A is similar to B if there exists an invertible matrix P such that AP is equal to PB or B is equal to P inverse AP. Okay. So, one thing is very obvious from this fact. So, what is that? That determinant of B and determinant of A are equal. This is very clear from here. You can see that determinant of B will be determinant of P inverse AP, and that will be equal to determinant of P inverse, determinant of A, determinant of P, since determinant of A into B is equal to determinant of A into determinant of B. Now, determinant of P inverse is 1 upon determinant of P into determinant of A into determinant of P. So, these two cancels out. So, it is equal to determinant of A. So, what we obtain? The first property of similar matrices is that if two matrices A and B are similar, then their determinant are always equal. This is the first property of similar matrices. The second property is that if two matrices are similar, then they have same eigenvalues. Okay. So, how can we prove this? So, if A is similar to B, this means implies there exists P such that AP is equal to PB or A is equals to PB P inverse. Okay. If A is similar to B. Now, we have the second property, we have to show that if two matrices are similar, then they have same eigenvalues. So, how we can proceed for this? Suppose Ax equal to lambda x, where x is not equal to 0. So, what does it mean? This means that A has an eigenvalue lambda and the corresponding eigenvector is x. Okay. Now, since A is similar to B, that means A is equal to PB P inverse. So, you can replace A by PB P inverse. Okay. Now, this implies B into P inverse x, this we can easily write. You pre-multiplied both the sides by P inverse because P is invertible. So, it is P inverse of lambda x, and this implies B into P inverse x is equal to lambda times P inverse x. Okay, because lambda is a scalar, can be taken out. Now, this P inverse x, you can suppose let this P inverse x is y, suppose, then this is B y equal to lambda y. So, what we have concluded? We have concluded that B matrix has an eigenvalue lambda and the corresponding eigenvector is y. In order to prove that y is an eigenvector, you have to show that y is not equal to 0, of course. So, that is very easy to show. Suppose y is equal to 0, we can prove this by contradiction. If y is equal to 0, that means P inverse x equal to 0. Now, x is not equal to 0, x is not equal to 0 from here because it is an eigenvector, and this matrix is invertible. This is a system of linear equations. Okay. And system of linear equation with this matrix is invertible, that means only unique solution, which is x equal to 0, but x is not equal to 0. So, it is a contradiction. Okay. because from here it implies that x equal to 0, which contradicts that x is not equal to 0. Hence, y is not equal to 0, because whenever we write such expression that by equal to lambda y, if y is not equal to 0, then only we can say that the eigenvalue is lambda and the corresponding eigenvector is y. Okay. So, what we have concluded basically, we have taken a matrix A with eigenvalue lambda and the corresponding eigenvector x, and using the property of similar matrices, we have shown that a matrix B has the same eigenvalue lambda and the corresponding eigenvector is y. Okay. So, we can say that similar matrices have same eigenvalues. Of course, their eigenvector may not be same. If x is an eigenvector corresponding to lambda here for A, then corresponding to lambda for B, the eigenvector is y, which is P inverse x. Now, if they have same eigenvalues, this clearly shows that the characteristic polynomial of similar matrices are same, since roots are same. If roots are same, eigenvalues are same, that means characteristic polynomial of matrix A and B, which are similar to each other, are also same. Okay. Now, since they have same eigenvalues, that means the trace of the two matrices are also same. Trace is nothing but sum of eigenvalues. Now, if the similar matrices are same eigenvalues, that means sum of eigenvalues are also same, and this implies that trace of two matrices are also equal. Okay. So, what we have concluded? We have concluded that if two matrices A and B are similar, then their determinant are equal, then their traces trace of the two matrices are equal. Trace of A is equal to trace of B, where A and B are similar matrices. They have the same characteristic polynomial, and hence they have the same characteristic roots or eigenvalues. Okay. Eigenvectors may not be same. Okay. So, these are what they are in this properties. You can easily see if two matrices represent the same linear operator, if and only if the matrices are similar. Number 1, if matrices are similar, then the linear operators are also same, or if they have the same linear operator, then the matrices are similar. If A and B are similar matrices, then determinant are equal, trace are equal, same characteristic polynomial and same eigenvalues. This we have already discussed. However, eigenvector corresponding to an eigenvalue for a similar matrix A and B may be different. In fact, if x is an eigenvector corresponding to an eigenvalue lambda of a matrix A, then P inverse x will be the eigenvector corresponding to lambda for the matrix B. Okay. This we have already discussed. Now, let us discuss one example. Suppose A is this matrix and B is this matrix. Okay. Then A and B are similar. How we have concluded this? This is very easy to conclude basically. If you have two matrices A and B, any two matrices A and B, okay, you have to check whether these two matrices are similar or not. So, you basically take arbitrary matrix P such that AP is equals to PB. Okay. Here A and B are 2 cross 2 matrices. So, you can take P as A, B, C, D. Then you can solve the left hand side, you can solve the right hand side, okay, and you will get 4 equations in 4 unknowns. You can find A, B, C, D, and if you find A, B, C, D such that this matrix P is invertible, that is AD minus BC is not equal to 0, that clearly means matrix A and B are similar, because we have shown the existence of such P such that such invertible P such that AP equal to PB. So, here also you can find such P which we are getting as this. You can easily verify here that B equal to P inverse AP. So, we can say that these two matrices are similar. You can also verify here, you can see the trace is 10, here the trace is also 10, here the determinant is 24 minus 6, 24 plus 6, 30, and here also if you simplify you will get 30, the determinant of P, because they are similar. Now, in terms of linear operator, What do you mean by diagonalizability? So, if T is a linear operator on a finite dimensional vector space V, then we say that T is diagonalizable if there exists a basis for V, each vector of which is a characteristic vector of T. So, what does it mean? It means that there exists a basis S which is given by u1, u2 up to un of V, for which T of u1 equal to lambda 1 u1. It is something like Ax equals to lambda x. We already know that every linear transformation corresponds to a matrix with respect to some basis. So, if this is a basis, and so T of u1 will be lambda 1 u1, T of u2 will be lambda 2 u2, and so on, T and un will be lambda and un. Then T is represented by a diagonal matrix D, which is given by this. So, what does it mean? We will discuss later on by taking an example of matrices. So, the linear operator T is diagonalizable if the matrix representation of T, that we already know that every linear transformation represents a matrix. Okay. So, if a linear transformation, if a matrix representation of a linear operator T is similar to a diagonal matrix D, then we say that T is diagonalizable. That clearly means that the matrix representation of T is similar to D, that means there exists an invertible matrix P again such that matrix representation of T is equal to P D P inverse. So, what we have concluded? We have concluded, suppose we have a matrix A, which is a matrix correspond to a linear operator, matrix representation of a linear operator T. Then we say that this matrix is diagonalizable if it is similar to a diagonal matrix D. D is a diagonal matrix, okay? Diagonal D1, D2 up to Dn. If A is n cross n matrix, okay? It is similar to a diagonal matrix means there exists an invertible matrix P, okay, invertible matrix P such that AP is equal to PD, or A is equals to PD P inverse. Now, we know that eigenvalues of A and eigenvalues of its similar matrices are, eigenvalues of similar matrices are same. This we have already proved, okay. So, and it is a diagonal matrix, and the eigenvalues of diagonal matrix are nothing but the diagonal elements itself. So, we can say that here the diagonal elements of this D are nothing but eigenvalues of A. That means, if A has an eigenvalues lambda 1, lambda 2 up to lambda n, then this D will be nothing but lambda 1 0 0 0, 0 lambda 2 0 0 0 and 0 up to lambda n, because similar matrices have same eigenvalues. Okay. Now, if characteristic polynomial P lambda of T or of A is a product of n distinct linear factors like this lambda minus a1, all have a power 1, then T is always diagonalizable. If it is a distinct linear factors and all have a power 1 in the characteristic polynomial, then T is, or matrix is, always diagonalizable. Now, let us discuss algebraic and geometric multiplicity of a eigenvalue and eigenvector. So, what does it mean? Let us discuss. Okay. Suppose A is 5 cross 5 matrix and its characteristic polynomial is, suppose lambda minus 1, lambda minus square cube and lambda minus lambda plus 1, say, okay. So, it is 3 plus 2 is 5. Now, corresponding to lambda equal to 1, there is only one factor. So, we say that algebraic multiplicity for lambda equal to 1 is 1. Algebraic multiplicity means number of times that lambda repeats. This lambda equal to 1 is repeating only one time. So, algebraic multiplicity corresponding to lambda equal to 1 is 1. Now, this lambda equal to 2 is repeating 3 times. So, we say that algebraic multiplicity corresponding to lambda equal to 2 is 3. Again this lambda equal to minus 1 is repeating one time. So, we can say that algebraic multiplicity for lambda equal to minus 1 is 1. So, algebraic multiplicity corresponding to a lambda is nothing but number of times that lambda repeats. Okay. Now, corresponding to this lambda equal to 1 or lambda equal to 2, suppose lambda equal to 2, corresponding lambda equal to 2, number of linearly independent eigenvectors are suppose k. Of course, k will be less than or equal to 3. Okay. Now, suppose number of linearly independent eigenvectors corresponding to this lambda equal to 2 are k. So, this k is called geometric multiplicity for lambda equal to 2, geometric multiplicity corresponding to lambda equal to 2. So, geometric multiplicity is nothing but number of linearly independent eigenvector corresponding to a lambda. Okay. Now, geometric multiplicity which is GM corresponding to a lambda is always less than or equal to algebraic multiplicity corresponding to that lambda. It can't be more than this. Now, since lambda equal to 1 is repeating one time, so what is the algebraic multiplicity for lambda equal to 1 is 1, okay, for lambda equal to 1 for this particular example. So, GM for lambda equal to 1 will be less than or equal to 1. So, GM will be 1 only, it can't be 0. There is at least one linearly independent eigenvector corresponding to a lambda. Okay. So, that means if a lambda is repeating only one time, so number of linearly independent eigenvector corresponding to that lambda will be 1 only. Now, here for lambda equal to 2, algebraic multiplicity is 3. So, what should be the geometric multiplicity? Geometric multiplicity will be less than or equal to 3, because by this property we can say that for lambda equal to 2, geometric multiplicity for lambda equal to 2 will be less than or equal to algebraic multiplicity which is 3. So, geometric multiplicity of for corresponding lambda equal to 2 either is 1, 2 or 3, and for lambda equal to minus 1, geometric multiplicity is 1. Okay. Now, what is a sufficient condition by which we can surely say that a matrix is diagonalizable or not? Because finding such P always for a bigger matrix, say 10 cross 10 or 5 cross 5, is not an easy task. So, what should be a sufficient condition by which we can surely say, seeing a matrix, that whether it is diagonalizable or not? So, what is that condition? Let us discuss here. So, this is an example. You see, here is 7 cross 7 matrix. Here it is lambda minus 2, lambda minus 3 whole square, lambda plus 5 whole raised to 4. So, for lambda equal to 1, algebraic multiplicity is 1. For lambda equal to 3, algebraic multiplicity is 2. For lambda equal to minus 5, algebraic multiplicity is 4. Geometric multiplicity is simply number of linear independent eigenvector associated with it. So, that is, it is a dimension of the null space of A minus lambda I. How it is, we will discuss by an example. So, this we have already seen that geometric multiplicity of an eigenvalue lambda does not exceed its algebraic multiplicity, number 1. Now, a matrix is diagonalizable if and only if geometric multiplicity corresponding to each lambda is same as its algebraic multiplicity. Okay. That means, if geometric multiplicity corresponding to each lambda I is equal to algebraic multiplicity, then only matrix will be diagonalizable. So, this is a sufficient condition. Or we can say that if a matrix has an order n, then it will be diagonalizable if and only if it has n linearly independent eigenvectors, because corresponding to each lambda, geometric multiplicity equal to algebraic multiplicity. Number of eigenvalues are total n. So, it must have n linearly independent eigenvector if matrix is diagonalizable, otherwise it will not be diagonalizable. So, let us discuss these two examples quickly, and from here we can analyze each and everything. So, what is the first example? The first example is, you see A is given to us as 3 minus 1 1, 7 minus 5 1, 6 minus 6 2. eigenvalues which is given to us are 2, minus 4 and x. Okay. It is given to us, or we can find out the eigenvalues by finding the characteristic polynomial of this matrix. Now, how we can find out x? X we can find out because the sum of eigenvalues is equal to trace of A, and trace of A is simply 3 minus 5 plus 2. Okay. So, it will be x minus 2 will be equal to it is 5 minus 5 0, that is x equal to 2. So, what are the eigenvalues of this A? Eigenvalues of A will be 2, 2, minus 4 because x is 2. So, what is the algebraic multiplicity of 2? Is 2, and what is the algebraic multiplicity of minus 4? Is 1. Corresponding to lambda equal to minus 4, geometric multiplicity will be 1 only, because geometric multiplicity is always less than equals to algebraic multiplicity. Now, corresponding to lambda equal to 2, if geometric multiplicity is equal to 2, then only this matrix will be diagonalizable. If it is less than 2, that is 1, then this matrix is not diagonalizable. Not diagonalizable means there does not exist any D such that A is similar to D. Okay. There does not exist any P such that AP equal to PD. So, let us find eigenvector corresponding to lambda equal to 2. So, eigenvector for lambda equal to 2. So, how you will find it? A minus lambda I x equal to 0. This implies lambda is 2. So, put it 2. This implies what is A minus 2 I? It is 1 minus 1 1. It is 7 minus 7 1. Okay. It is 6 minus 6 and 0 times x is means x1, x2, x3. If 0 means 0 0 0. Now, you can it is 1 minus 1 1, you can take one operation, that is this minus 7 times this is 0, this minus 7 times this is 0, this minus 7 times this is minus 6, this minus 6 times this is 0, this minus 6 times this is 0, this minus 6 times this is minus 6, and this minus this row will give 0 here. We are trying to make a Cleon form of this. So, what we have obtained from here? It is x1 minus x2 plus x3 equal to 0 and minus 6 x3 equal to 0. So, this implies x3 equal to 0. If you substitute x3 equal to 0 here, so we obtain x1 equal to x2. So, how many linearly independent eigenvector correspond to lambda equal to 2? It is only one, which is x1 x1 0 or 1 1 0. You take any one linearly independent eigenvector, which is you say 1 1 0. So, it is only 1 1 0, only one, that is geometric multiplicity corresponding to lambda equal to 2 is 1. It should be 2 for diagonalizability. So, we can say that this matrix A is not diagonalizable. So, how we can check? You see we have find the null space of this basically A minus lambda I. We are basically finding all these things means we have find null space of this matrix A minus 2 I. Okay. Or we can say that if R is the rank of the, you see rank of this matrix is 2, okay, and number of unknowns are 3 or order of matrix is 3. So, 3 minus 2 is 1 and 1 is the number of linear independent eigenvectors. So, that means if R is the rank of A minus lambda I and n is the order of A, then n minus R will be the geometric multiplicity corresponding to that lambda. And if it is equal to algebraic multiplicity for each lambda, then only matrix will be diagonalizable. Okay. Now, you can see here, you can see a second example here. Here A is 4 1 minus 1, 2 5 minus 2, 1 1 2. and here eigenvalues are 3, 3 and lambda. Let us see whether it is diagonalizable or not, and if yes, what will be P and how we can find the other expressions in this problem. Okay. So, this is the problem, let us try to find it quickly. So, the sum of eigenvalues again is equal to trace of A. So, lambda will be, it is 9 plus 2 11, 11 minus 6, that is 5. So, we can say that eigenvalues of this A are 3, 3 and 5. So, we will find number of linearly independent eigenvector corresponding lambda equal to 3. First we will check. Okay. So, for lambda equal to 3. So, for lambda equal to 3, it is A minus 3 I times x equal to 0, and this implies 1 1 minus 1, 2 2 minus 2, and it is 1 1 minus 1, x equal to 0. So, when we convert into Cyclion forms, we can easily see that it is 2 times this and it is 1 time this. So, it is 0 0 0 0 0 0 x equal to 0. So, what is the rank of this matrix? Rank is 1, and what is the order of the matrix? Is 3. 3 minus 1, that is 2. That means 2 is the geometric multiplicity corresponding to lambda equal to 3. So, yes, because algebraic multiplicity is 2 and geometric multiplicity is also 2, for lambda equal to 5 it is 1 only. So, that means this matrix is diagonalizable. Okay. So, what are those two vectors? X1 plus x2 minus x3 equal to 0. So, we can to pick any two arbitrary linear independent eigenvectors satisfying this equation. So, we can take x1 as 1 minus 1 0, because 1 minus 1 0 is satisfying this, and x2 as 1 0 1, and these two are linear independent. Is it okay? Because 1 minus 1 0 satisfying this and 1 0 1 also satisfying this, and these two are linear independent. So, yes, they will form the entire eigenspace. Okay. Now, corresponding to lambda equal to 5. For lambda equal to 5, again we can find out A minus I times x equal to 0, and when we simplify it is minus 1 1 minus 1, it is 2 0 minus 2, and it is 1 1 minus 3, x equal to 0, and when you simplify this you will get x as 1 2 1. You can find a Cyclion form, and then vector you find is this vector. So, how you can find out P? Because it is diagonalizable, now we have ensured that this matrix is diagonalizable. So, how we can find out that P? So, to find P, how we can find out P? We simply write first x1 vector here, x2 vector here, x3 eigenvector here. So, what is the x1 eigenvector? X1 eigenvector we have already find 1 minus 1 0, x2 is 1 0 1 and 1 2 1. This will be that P, and it is always invertible because eigenvectors are linearly independent. Okay. So, it is always invertible. Okay. So, what will be its P inverse? So, P inverse you can easily find out, and the P inverse which you can find will be 2 0 minus 2 minus 1 minus 1 3 1 1 minus 1. This you can find out the P inverse. Now, AP, so AP will be equal to PD, and this implies A is equals to PD P inverse. So, and what is D here? D will be nothing but what is the first eigenvector? First eigenvector is this x, and this is corresponding to lambda equal to, this corresponding to lambda equal to 3. Okay. So, here you can write first is 0 3 0 0 0. The second eigenvector is corresponding to again lambda equal to 3 C. Okay. So, it is 3 0, and the third eigenvector is corresponding to 5. So, it is 5. Now, suppose if you want to find out A square, say A square is nothing but A into A, which is equals to PD P inverse into PD P inverse, and this is nothing but PD P inverse P into D into P inverse. So, it is P D square P inverse. That means A square is also diagonalizable. Okay. Similarly, if you proceed like this, so what is A raised to power k? It is P d raised to power k into P inverse. Suppose you want to find out A raised to power 10. So, it is P d raised to power 10 into P inverse. And what is d raised to power 10? It is 3 raised to power 10, 0, 0, 0, 3 raised to power 10, 0, 0, 0, 5 raised to power 10. P you know, P inverse you know, d raised to power 10 you know. So, simply multiplication of these 3 matrices will give you A raised to power 10, which is otherwise we have to find out A raised to power 10 by 10 matrix multiplication. Suppose you want to find A raised to power 50, similarly you can find out A raised to power 50 also, P d raised to power 50 into P inverse similarly by the matrix multiplication of these 3. Okay. Now, suppose you want to find out E raised to power A, it is I plus A square by 2 factorial and so on. Okay. So, if you multiply P, you see here it is A equal to P d P inverse. Okay. So, here A is equal to P d P inverse. So, if you take P inverse E raised to power P into P, so this will be P inverse P plus P inverse A P upon factorial 1 plus P inverse A square P upon factorial 2 and so on. And this is identity plus it is D, because A is invertible, I mean A is diagonalizable, and it is d square upon factorial 2 as we have already discussed. So, it is E raised to power D. So, what we have concluded that E raised to power A is nothing but P E raised to power D into P inverse. And how P we know, P inverse we know, how we can find E raised to power D? E raised to power D is nothing but I plus D upon factorial 1 plus D square upon factorial 2 and so on. D is nothing but here it is lambda 1 0 0 0 lambda 2 0 0 0 lambda 3. Okay. Here lambda 2 and lambda 2 are 3 and lambda 3 is 5 for this particular problem. Okay. Now, square will be lambda 1 square 0 0 0 lambda 2 square 0 0 0 lambda 3 cube square upon factorial 2 and so on. So, when you club all these terms, so it is the first term is 1 plus lambda 1 upon factorial 1, lambda 1 square upon factorial 2, lambda 1 cube upon factorial 3 and so on, which is nothing but E raised to power lambda 1. Second term is 0 throughout, this is 0, this is again E raised to power lambda 2, 0 0 0 E raised to power lambda 3. So, E raised to power D we can simply find out E raised to power lambda 1 0 0 0 E raised to power lambda 2 0 0 0 E raised to power lambda 3. So, in this case E raised to power lambda E raised to power D will be what? E raised to power 3 0 0 0 E raised to power 3 0 0 0 E raised to power 5. So, hence we can find out E raised to power A also, E raised to power of a matrix by simply multiplying these 3 matrices. Similarly, if you want to find out sin A, sine of a matrix, this is a matrix not an angle, that also we can find out using the same derivation, same lines, following the same lines. Similarly, cos of a matrix, this also we can find out. So, these are some of the applications of diagonalizability. If a matrix is diagonalizable, we can easily find out higher powers of A by the multiplication of only 3 matrices, E raised to power A or sin A, cos A or other expressions of the similar types. So, in this lecture we have seen that when a matrix is diagonalizable, what are the important properties of diagonalizability and what are the some applications of diagonal matrices. Thank you.